said there's a couple of ways you could do this. Just put your calculator in the mode for radians and just substitute this back in. So in your calculator, you would say 2 cosine pi over 3 minus 1 equals, and if it says 0, then yes, it's a solution. You could put it in degrees, convert those to degrees and say 60 degrees, put your mode in degrees if you wanted to. Or you could also solve the equation. I don't think I would do that, but I mean, I did it here for you just in case. You could solve the equation and see, in fact, if those were your answers. So there were a number of ways just to check. The reason I included those in here is because trig equations are equations. And you can check your equations. You can always go back and check your answers to tell if it's wrong or right. So this is a good way to check them. The second one, the same thing. How do I put a secant in my calculator? How do I say secant?
Cosine of
1 over cosine. So 1 over the cosine of, and this is going to say pi over 3, minus 2. If it says equals 0, you got it. If you want to convert it to degrees, convert it to degrees. Secant is 1 over cosine. Cosecant is 1 over sine. Cotangent is 1 over tan. You could solve the equations, see if in fact they were the ones they were looking for. You could do it that way. There are a number of ways just so that you kind of understand that equations are very, very checkable. Okay. Yeah. Remember, we're no restrictions anymore. This is going on in all quadrants forever and ever because your curves go endless. They really have no beginning, no end. So first thing we do is we solve the equation algebraically. We get down to here and we say, okay, algebraically we're good. Now here's where my trig comes in. What angle has a sine of -1/2? So we say sine is y. Wherever y is negative, we drop 2 triangles. And we know that it's this guy, which is 7 pi over 6. This guy, which is 11 pi over 6. Now, because we said sine is negative in 3 and 4, sine is y over r. So this is a 30-degree angle, right?
Yeah.
So 30 goes into 186 times this is 6 pi over 6, 12 pi over 6. So the one right after 6 is 7 pi. The one right before 12 is 11 pi. If you want to convert to degrees and then later convert them to radians, it's a little bit more work, but if that's what you like to do. Now, we wanted all solutions. So we said on Friday, all solutions means that not only just 360 degrees, but if it went another 360, and another 360, and another 360, and it kept on going. So if my original thing was here, I had to go another 360 to get here, another 360 to do another one, and again another 360. So 360 is the same as 2 pi. So I keep adding 2 pi each time. And I increment my 2 pi's by n. So the first time around I have none. I'm in the original set of quadrants. Then I do n is 1. I've gone another 2 pi around. Then I do n is 2. I've gone 2 pi around again. So the way we qualify that is plus 2n pi, where n is any integer. This takes all solutions in here. So if we're looking for all solutions, you're going to locate your quadrants that they come in. And if they're just like opposites of each other, just do plus 2n pi. Because you want all possible solutions. God bless you. You okay with this? Okay. No? Yes?
Come on, if you have trouble, come on. Answer this more too.
Thank you, babe.
Well,
Okay, so at least I have youth in my life that I'm here for you guys. to help you out. Okay, we solve algebraically. Algebraically, our variable is sine of x. We get all the way down here. We solve sine of x. So now we look at the trig part. Again, we say, where is sine negative? Sine is negative where the y is negative, quadrants 3 and 4. We label our triangle. We say, well, this is a 45-degree angle. This is the last part of trig that you still have to remember that. So 4 pi over 4, 8 pi over 4. So this goes to 5 pi over 4. And this guy goes to 7 pi over 4. But since we wanted all solutions, we say, okay, from here, add 2 pi. From here, add 2 pi. So we qualify all solutions with plus 2n pi, where n is any integer. Because we keep adding 2 pi, and add another 2 pi, and add another 2 pi. Keep on going endlessly. It's your sine curve. Your sine curve, don't forget, goes on and on and on and on and on and on and on. Negative and positive, so even if we put a negative 1 in there, it would bring us back to this side, and then this side. We'll get every solution possible. Good? All right. Then we did a secant one. So algebraically, you're going to solve all the way down to here until we did all the algebra, then the trig comes in. Now we talked about secant being a reciprocal. If you rather look at the cosine, take that reciprocal, take that reciprocal. Radical 3 over 2? That's probably more recognizable than 2 over radical 3. Although I recognize the parts of 2, I recognize the parts of radical 3, I can recognize the parts. That, oh, this must be a special triangle. Now, cosine uses the x values. So it's positive over here in 1 and 4. Again, set it up. There's your 3. So this guy is 6 pi over 6. This guy is 12 pi over 6. So we have one original 1 pi over 6. And one that comes all the way back around, 11 pi over 6. And again, we add 2 and pi, 2 and pi, 2 and pi. We just keep adding 2 pi to it. Got quiet. Is this good? Okay. Yep. Now, cotangents, a little bit different for cotangent. Cotangent, we solve algebraically, and we say, oh, what angle has cotangent of -1? Well, tangent is the same thing. Reciprocal of -1 is still -1. So, tangent of 1, ring a bell to your angle. What angle would that be? Tangent of 1. 45-degree angle. Very good. So, negative in quadrant 2 and 4. So we know this is a 45-degree angle. We say, what guy is this? This is 3 pi over 4. We say, what one is this one? One less. We say 7 pi over 4. Now, here's the problem. We could list both angles, and we could say plus 2n pi. But, not that we have a problem, but they're really 180 degrees from there. If I add 180 to this guy, let's call this 135 in degrees so that you can see it. If I add 180 degrees to this, I will be at 225. Sorry, 325. Sorry. Isn't this same angle at 325? So if I add 180 degrees when I'm completely across, I will get all my solutions. So 180 degrees is the same as pi. So now I just have to list this one and add n pi, and add n pi, and add n pi, and n pi. I'll keep going 180 degrees around because it's directly across from each other. If they're next to each other, can't do that. Can't add 90, can't add 180, can't add anything else there. I have to do the 2n pi, such as this guy. I have to come back to this one again. I have to come back to this guy again. But if they're across from each other, I can add n pi. Talk to me if you're having any problems. All right? Now, here's another unique situation. Secant, I solved algebraically. I'm coming down here. I have to take the square root, so I isolate this. I divide by 4, 4 divided by 3. I then take the square root, you get a positive and negative, and separate this. This gives me 2 over radical 3. We just saw 2 over radical 3. So we flipped it over, we took its reciprocal to make it a little bit easier. We looked at the cosine. Now, because we have a positive and negative, we have all 4 quadrants. All I care about is finding one reference angle. I find my one reference angle. This is radical 3, this is 1, this is 2, this is a 30. So I say 6 pi over 6, 12 pi over 6. Because they're across from each other, if I name this guy 180 degrees away, I can name that one, right? So I name this one and add n pi. Then I didn't touch this one yet, so I come across, I'm 1 short of 6, I'm 5 pi, and if I go 180 degrees across plus n pi, I name the other ones. This is what's going to give you all solutions. If you gave me all 4 angles and you said plus 2n pi to each one of them, is it wrong? No, it's not wrong. So if you don't see it as n pi, you can still keep the 2 pi. It just will be a little harder later, but it's still not wrong. Good? Cotangent again, if you prefer to look at tangent, when you come down here, you can take this reciprocal, plus or minus this reciprocal. Tangent is y over x. If you can, in your mind, flip it to x over y. Again, you have all 4 quadrants. So find the first one, pi over 3, and add n pi. Then find the second one. This would be 3 pi over 3, so this is 2 pi over 3, and add n pi. This gives us our all solutions. This is what's different from last year. Last year, you only really had to go to 2 quadrants. Pretty sure you only did just the all 4 quadrants. You just do the regular 0 to 2 pi. But this is different. And if you take this in college, this is what they're going to be looking at. Right. And I think this is your last one. Again, cosine squared, by the time you take the square root, you got all 4 quadrants. Don't forget to separate this, or if you don't separate this, what happens is it's never going to come out to something you know. Don't leave it under the radical. So separate it, plus or minus 1/2. Oh, that tells me 60 degrees. So again, just like the last one, 3 pi over 3, 6 pi over 3. You got to hit this one and 180 across. Then you're going to hit this one and 180 across. And as any integer. And just qualify them with n as any integer. Just say it once. Alright, so again, if you struggle with this, my advice is take it out for a minute. Just use variables in there. Just so that you can see, because I know kids end up seeing cotangent, cotangent, and how many kids I see say divide by cotangent. Don't divide by your factors, ever. Don't divide by your variables. Factor it out and set them equal. Good? Okay. Let's try another one. This one has an all solutions from 0 to 4 pi. So whenever you see an all solutions besides the 0 to 2 pi, we're going to find our all solutions first. and then we're going to work the 4 pi. So I notice this is my variable. So I'm going to take this out a minute and let it look like this. How would I factor this trinomial? 2 binomials. I know the 1 has a factor of 1. I know my 2x, my 2 only has one set of factors, 2x and 1x. And my signs have to be what? One positive, one negative. God bless you. So one positive, one negative, maximum 2 times to get the factors. If you put them in wrong the first time, swap them, and they'll be right. I need my larger product to be negative. So these are your middle terms. They make a little smile. So my first one, if I put a negative here, this would become negative, this would become positive. I don't want that. I want this guy to be positive, this guy to be negative. Only going to take you maximum 2 times to get that one. I realize A is not 1, but C is 1. And A only has one set of factors. Remember, we're not going to find large factors in here because your sides of your triangles or your quadrants, 1s and 0s, 2, maybe 3. This is my smile.
No. That's where it's equal.
Oh, equals 0. Okay, so now we're going to do the same thing here. We're going to put 2 sine x plus 1 sine x minus 1. Again, 2 sets of factors. Solve them both separately. These take a little bit more work. You got 2 things going on. So subtract 1, divide by 2. Add 1. So let's find all solutions first. So from 0 to 2 pi, where am I negative? Where is sine negative? Sine is which one, the y or the x? The y. So go to the y negative down here. So sine is negative here and here. Y over r, what's my reference angle? 30. So 30 goes into 180. So this is 6 pi over 6. This is 12 pi over 6. So I come all the way around to this guy. How do I name him? Good. 7 pi over 6 plus 2n pi. We'll qualify this in a second.
Wait, why'd you plus 2n pi?
Because we're going to go for all solutions first. Then this guy is what? 11 pi over 6 plus 2n pi. Now, we have 2 ways we could do this. Since we only have to go to 4 pi, if we have 2 of those angles in 2 pi, how many will we have in total in 4 pi? 4. So, if I wanted to, I could keep this pattern going. This went to 6, 12. If I add another 6, what would this be? 18 pi. If I add another 6, since I only have to go to 4 pi, I could absolutely do it this way. I could say 7 pi over 6. These are my original, 11 pi over 6. Then one more after 18, which would be what? 19 pi over 6. And 23 pi over 6. Good. That will give me my 4 pi. Or I can do this. I can take my x equals 7 pi over 6 plus 2n pi. And I can say, okay, see this denominator 6? Convert this guy to 6's into 6. So if I multiply 1 times 6, I have to multiply 4 times 6, right? This is just telling me I'm going to go up to 24 pi over 6, and then I have to stop. So, or I have to stop right before that, actually, because I can't use that one. So now, your 2 pi, convert this one to the same denominator. So what is 6 times 2? 12. So every time I do this, I'll add 12 pi over 6 to 7 pi over 6. So I'm going to start at 7 pi over 6, add 12 to your numerator, because now your denominators are the same. What is 12 plus 7? 19 pi over 6. What is 12 plus 19? 31. Aren't I over the 24? So I can't use that one. Start the 11 pi over 6. Add 12. 11 plus 12 is what? 23 pi over 6. If I add another 12, won't I be over the 24? And doesn't this make sense? If I have 2 and 2 pi, I should have 4 and 4 pi.
So, with the answers like pi over 6, 11 pi over 6, 19 pi over 6, 23 pi over 6, be right?
It is right. And if you can do it that way, or you can do it this way.
So why do you put the,
Start off like this. Start off as all solutions, because you can always keep adding them here. Because sometimes we'll say to 0 to 4 pi, sometimes we'll say 0 to 8 pi. We can keep doing this. But my point with that is, since we only had to go around the circle one more time, it's probably easier if you get that pattern of sixes, do it there. And you don't have to do this part. If you like to, that's fine. Now, we didn't finish this guy. Sine is 1. I notice my sine is 1. Sine is the x or the y? The y. So in my quadrants, where is sine 1? 90 degrees. So this guy up here is pi over 2. Now, you could say plus 2n pi, and then you would give me x is pi over 2. Now, if you're only going to go around one more time, count. This is 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. If I add what does my denominator have to be? God bless you. 2. 2. So what is 2 times 2? 4. So I'm adding 4 to this 1. Aren't I going to get 5 pi over 2? And then I'm going to have to stop, because if I convert this to 2's, this would be 8 pi over 2. And I got to stop. So you have these 4 and these 2 as your solution. Make sense? Well, you only have to give me the 0 to 4 pi. So this is what I'm looking for in the end. If you can keep rotating around, then you don't have to do the plus 2n pi. If that's troubling, start everything with all solutions, and then just keep adding it until you hit the limit. Either way you decide to do that is fine with me. When we get a lot of angles, you're going to do the 2n pi routine. But since this is only giving us 4, and in this case 2, we can count. We good with that? All right, one more. Ready? Now, let me look at my variables. I have a sine, and then I have a cosine. They're different, aren't they? So I'm going to make this say 2 y squared, there's my variable, plus 3 cosine, there's my variable, minus 3 equals, oops, I should have done this in red, 0. There's one variable, there's one variable. In this case, can I solve this? Can I factor them with 2 different variables? No. So I'm not able to do this. However, in trig, there's a little special identity that you have called Pythagorean's identity. Here's my unit circle. It's a 1. There's my x, there's my y. X squared plus y squared equals 1. And on a unit circle, the cosine is the x, the sine is the y. So Don't I have this nice little identity? Cosine squared plus sine squared equals 1. So can't I substitute out one of those? Which one can I substitute out? So I can't get rid of cosine x because that's the lowest it could go. But I notice for sine squared x, if I solve this for sine squared x, I subtract cosine squared x, I get 1 minus cosine squared x. So if I take out the sine squared x, can I substitute in 1 minus cosine squared x? I'm going to take this out and put 1 minus cosine squared x. I cannot do anything with a cosine or a sine, just a square. Because I have Pythagorean identity. It's Pythagorean's theorem with your sine and your cosine in there. So now, let's distribute. Notice you're all on one side of the equal sign. When you're on two sides, yeah, you can subtract and add to the other side. When you're on one side, collect your like terms. So, this is my highest term. This is my next highest term. What is 2 minus 3? -1. Now I want to factor this guy. But remember, I don't like to factor when a is negative. So how can I get rid of that negative sign? Take out a -1. Divide or multiply by a -1. Just change everybody's signs. So now I can factor. 2 cosine factors into cosine times 2 cosine. What does 1 factor into? 1 and 1. This is why I say you don't get a lot of choices. Like there's not a lot of factors because your numbers are so small. What signs do I need in here? I need to multiply to get a positive, add to get a negative. Two negatives. Good. So when I multiply, won't I get a positive? When I add, won't I get a negative? Now I have two factors. Separate them. I have 2 cosine x minus 1 equals 0. And I have cosine x minus 1 equals 0. Okay. We can just solve this for all solutions to make life easy. So I add 1, divide by 2. See how we're kind of seeing the same things over and over again? You only have 2 special right triangles. The 1, the 2, the radical 3, and the 1, the radical 2. And then you have quadrant which are 1s and 0s. And so this guy, so let's work on this one. Where do I find cosine positive? Cosine is my x value. 1 and 4. Good. So cosine is x over r. This is radical 3. What's my reference angle? Who's opposite the radical 3? 60. Good. So this is 3 pi over 3. This is 6 pi over 3. So let's name these angles. The first guy, pi over 3, plus 2n pi. And who's the second one?
11. 5 pi.
5 pi, good. Plus 2n pi. Okay, so we have 2 for those. I don't know if you can see that. We said x is equal to pi over 3 plus 2n pi. And x is equal to 5 pi over 3 plus 2n pi, where n is any integer. Now we got one more, cosine of 1. So on my unit circle, my cosine is my x value. This guy would be a -1. So therefore, I've got 0 degrees plus 2n pi. So you can just say 2n pi. So at the 0, the 2 pi, the 4 pi, the 6 pi, the 8 pi, I will always find cosine of 1. So I've got these as my solutions. this and this is the same. Okay? Make sense? So on the homework, you're going to have some that go from 0 to 2 pi. Actually, they all go to 0 to 2 pi. Just because these are probably a little harder to deal with, so you're only in quadrants 1 through 4. And then tomorrow we'll throw little all solutions in there.
So if it's 0 to 5, then we don't have to.